Hello, everyone. Again, thanks for joining our webinar series on the high resolution land model and the land atmosphere coupling. And it's our first one in 2025. And it's our pleasure to have one of our panelists, Stefan Kollet, to share with us those high resolution groundwater modeling in the land source model and also in earth system model, which that Stefan has worked on this in the past 1 or 2 decades, I would say. And before Stefan start the webinar, let me introduce briefly about Stefan. So Stefan right now is a professor in the integrated modeling of terrestrial systems in the Institute of Bio and Geoscience in the research center in Jülich in Germany, and also a professor in the Department of Meteorology in the University of Bonn in Germany. And where Stefan got his PhD from University of Nebraska, Lincoln in the United States. After he obtained his PhD, then he went to the Lawrence Livermore National Laboratory for a postdoc researcher and also scientist. And then in 2011, 2012, also worked as a senior computational geoscientist in Netherlands. Then went to Germany as a professor till now. Then Stefan's research expertise is in groundwater modeling. Then using this high resolution groundwater modeling in Lenses model, coupling with Lenses model, also discuss how this will affect the regional climates. Then today is our pleasure to have Stefan to give us this latest research on the groundwater modeling. So let's welcome him.
Yeah, thank you very much, Min-Hui.
Yes, you can share your screen now.
Will try to share my screen. Second, is it working? Not yet. Let me try this again. Here we go. Okay, yeah, thank you very much for this kind introduction and for giving me the opportunity to present some of our latest work. So I'm going to talk today about groundwater representation and high resolution land and also earth system modeling. And I would, of course, like to acknowledge all my colleagues that have been working with me over the past, yeah, like you said, like almost like decades, right? On this, and we get to some of my colleagues, during the presentation. So what I want to cover today is first I want to talk a little bit about the motivation, why we want to have high resolution groundwater modeling in land modeling and also in earth system modeling, and then talk about the trends that we currently have, and then make the case for prognostic PDE-based high resolution modeling that I will present also some very new simulations that we perform now at the global scale. So you have seen this slide before, of course, many times, and I don't want to go
Stefan, I don't think we're seeing the slides. They came up and then disappeared. Are you still sharing?
Yeah, I can see it. Can you see it? Can you share it again?
I can try, yes.
Okay.
So do you see them now?
Yes. That's great.
I see them.
Yeah.
Yep. Perfect.
Okay, let's try it again. So yeah, so you have seen this kind of conceptual schematic before many times, and I don't want to go into details here. I just want to highlight a couple of important things. So we know that we have generally moist advection from the oceans onto the continents, and then over the continents we generally have larger precipitation than evapotranspiration. And it's important to understand that this actually also holds over quite arid regions. So what the continent has to do is the continent has to get rid of usually excess water. And so it has to basically move water from the recharge zones in the mountains towards the discharge zones, or the ultimate sink, the ocean. And of course, what we know is that rivers here play a major role. So the continental rivers actually drain our continents from the source area in the mountains to the sink areas, the oceans. But of course, it's not only the rivers, but it's really, in fact, groundwater actually that sustains our dynamic equilibrium or water equilibrium in the continents via base flow. And even in this kind of sophisticated, let's say, schematic, it's not really obvious that really it's as a matter of fact groundwater that maintains that equilibrium. So there is actually very little direct runoff on the surface. Usually, we know that the majority of water is really drained via the subsurface toward the continental river corridors, and then almost like the rivers acting as outcrops to groundwater, the water is then transported towards the ocean. And that's very important to understand. So groundwater is really key in maintaining that equilibrium. And of course, this kind of very delicate equilibrium is currently changing a lot. So we have the change in the source areas because of the snow ice regime that is changing strongly, and also, of course, because of evapotranspiration. And then, of course, we also have, along the oceans, we have the base level change. Actually, we have sea level rise that is also propagating into the continent. Then, of course, we also have the human influence that can be quite strong in terms of here depicted as a groundwater abstraction. So what we know is that we have this delicate equilibrium, water equilibrium, and now this is changing because of the changing snow ice regime in the mountains and what's happening at the ocean. So in between, really, the flow paths will be changing, and also exchange with the land surface will be changing, in the mountains and also along the coasts. And for that, we really have to consider groundwater at different scales. We see local flow patterns, but we also see the deeper flow path that will be changing on the order of decades or hundreds of years. So the key is here really groundwater is important in maintaining that dynamic equilibrium. So what's the current trend in ESMs? What we observe currently is that ESMs go to ever increasing resolution, and there's a clear expectation of why this is done. The idea is really to resolve, for example, better weather generating processes. And the expectation is that we can actually reduce biases also in global circulation patterns because of that increased resolution. And it's not only that we increase resolution just because that's what we can do. No, because we also have to really change the physics in the models. And this is really important to understand. If we go to, for example, kilometer scale resolution, then the physics of the model and the microphysics really change as well. So we have to actually then resolve more biogeophysical and also biogeochemical processes related, for example, to the carbon, nitrogen, phosphorus cycle. We have to resolve ice sheets much better. And of course, we also have to account for groundwater because we suddenly resolve really also very small scale river corridors. And of course, we also have to include human interventions, for example, pumping, irrigation, and also reservoirs. And of course, there's also AI is playing a big role here, and I get to this also towards the end. So what my argument here is really that groundwater is needed in Earth system models for feedback simulations. And this becomes really important at kilometer scale resolution. Of course, people have recognized groundwater for quite some time, also in the Earth system modeling community. And there have been a lot of efforts actually to implement groundwater in land surface models that are then, constituting the lower boundary condition in, for example, atmospheric models and Earth system models. Here, an example from Linda Schlemmer and Christoph Scher's group that implemented in Terra a gradient-based groundwater model that also is able then to account for convergence along river corridors. And very similar implementations have been done, for example, in also other land surface models, like, for example, NOAA-MP. Okay. So if you go take the other perspective, let's say, and you look into this from the more global water model perspective or hydrology perspective, there has been also some push for global groundwater modeling at also very high resolution. For example, here a study on the graph on environmental flow limits, and here on the right-hand side by Robert Reinecke on the uncertainty of groundwater recharge at the global scale. And what you observe here really is that, well, that first of all, that there is, for example, with respect to recharge, there are large uncertainty between different models, which are extremely difficult to reconcile. And what you observe here on the left-hand side, you see that these models actually have to account for estimated head declines on the order of centimeters or tens of centimeters over very large areas to come up with a strong conclusion. And of course, when you look at the associated uncertainties in these models, you know, it's very difficult to reconcile this kind of accuracy with the uncertainty. Also related, of course, with hydrologic heterogeneity. And this also propagates in other variables, diagnostics variables, for example, here in terms of water table depth estimates from different global water models. And you see here that over large areas, we have uncertainties on the order of tens of meters, but in some regions that are also very relevant in terms of water security, we see that the uncertainty can go up to tens of meters, even 100 meters. Okay, so there are structural model differences in parameterized global water models. And when you look at these studies, you actually realize before asking the question with respect to let's say, parameterization or structural, with respect to input uncertainty, with respect to, for example, the atmospheric forcing, and also the hydrologic representation in these models, we feel that it's very important to really understand what the structural model differences are, because these models are parameterized. When you look at these results at the global scale, this really leads to large skepticism with respect to large-scale global groundwater modeling in the hydrogeologic and groundwater model community. And there are many reasons for this. As well, the argument is, well, groundwater is a local to regional scale process, so maximum maybe to the continental scale. Why? Because there is no real global groundwater circulation. And it is actually impossible to do because, well, we have these huge challenges with respect to 3D heterogeneity in the subsurface. Water level measurements are lacking, water use information is lacking. And of course, if you do this really with PDE-based, physics-based models, the compute becomes huge. But we argue now that actually the benefits outweigh really the skepticism and the challenges. If we do this, let's say with prognostic PDE-based models, we get physical consistency. So we're really able to close the water cycle from the source areas to the sink consistently in terms of physics, and also actually with terms of solutes. We are able actually to connect to in-earth system models, also to the land surface and the atmosphere. So we can do actually bedrock to top of atmosphere simulations in a physically and also biogeochemical consistent way. And we are doing this already at the continental scale. We have spatial temporal continuity, which actually leads really to comparability and also transferability of the results, which, you know, will help tremendously in community building and communication. And also when we go to the global scale with PDE-based prognostic groundwater models, we can contribute directly to ESMs. And that way we can also get a global mandate, right? So, and I want to give you one example of a model in the comparison study where we compared 7 different groundwater models or integrated hydrologic groundwater models. Most of them were really PDE-based. Some of them were parameterized. And what you see here is, for example, a short time series, and you see here saturated storage. In this case, aggregated over the computation domain. Here you see it in terms of unsaturated storage. And what you observe actually throughout this kind of intercomparison is that the PDE-based models, they give a very consistent response because of their because they are grounded really in a combination of continuity and movement equations based on a physical rationale. Okay. Move on. And of course, there is also, when you look into these large-scale studies of hydrogeologic and groundwater flow modeling, based on these PDE-based approaches, you see that there's a lot of work going on here, for example, from colleagues in the UK that developed a national scale, very sophisticated 3D groundwater model and hydrogeologic model. We have been doing this over the European continent, over the European Cortex domain, also a kilometer scale resolution in 3D in terms of a continuum approach where we can compare very favorably, for example, here also to Grace anomalies. We have colleagues, of course, Reed Maxwell and Laura Condon, and colleagues who are doing that over the United States, also a kilometer scale resolution. We have sophisticated integrated hydrogeologic and groundwater flow models in China, the national groundwater model of China coming out of Chun Miao Zhang's group. We have that also over Africa. These are, again, colleagues from the USGS and South Africa who developed these continental scale hydrogeologic models and groundwater flow models for water safety and security assessments. And the USGS, of course, is doing a lot of work in this regard, also at the CONUS scale. And this is a very nice example where you have a large-scale groundwater flow model over the northern high plains, which is also coupled here with the community land model from NCAR to arrive at and other land surface models to arrive at improved recharge estimates. So there is a big push in this direction, and I think we have to make use of this in the near future. So yeah, again, I make the case for prognostic PDE-based global groundwater modeling. They have a clear physical and mathematical basis, a combination of continuity and movement equations, plus boundary initial conditions. There's often some concerns with regard to the validity at scale. There is actually, when you look into the literature of groundwater flow modeling, scale consistency over a very large range. And what we do right now is we are actually approaching also the support scale in the simulation of the equation. And I feel that actually currently parameterized models do not necessarily offer better scale and structural consistency. Of course, there's a lot of concern with respect to input and validation data, which is often considered prohibitive. I feel this is an immense challenge, but there are data sets. People start collating these, making them publicly available. And we are actually getting more and more very sophisticated interpolation techniques where we have huge potential of with respect to AI, which we have to mine actually. And I feel that the data challenge will never go away, and it's not a reason not to go for high resolution groundwater modeling at the global scale. Also, often what I hear, computational challenge is prohibitive. No, it's not. The compute is there. We know how to implement our codes on massively parallel HPC resources. We just have to do it and use it. And it's not a reason to reject prognostic models. So bottom line is I feel PDE-based continuum models are physically consistent, and this is a good reason to scale them up to the global scale. I want to come up with some definitions here that we used also in our community and in our literature and also in the coming slides. So we talk about the subsurface as a continuum, and this continuum consists of 3 phases. We are talking about the solid phase, the liquid phase, and the vapor phase. It's the matrix. In this case, it's groundwater and it's air. We're not talking about oil movement or gas movement or natural gas movement. We are really confining ourselves to the liquid groundwater phase and the air phase. So the matrix in the subsurface from top to bottom, from land surface down, it's a continuum. It's It's characterized by strong heterogeneity at all scales, and we describe that matrix in terms of hydrophases. So we basically have different types of matrix that can be based on lithology or pedology, and we try to describe this distribution of this hydrophases and associate certain hydraulic parameters to the different hydrophases. What you see here, for example, on the right is an example of a study by Reed Maxwell and colleagues, where we characterize the subsurface down to more than 300 meters, and where we basically developed a hydrophases distribution also based on geologic information and transition probabilities. Groundwater is again, it's a continuum, and it's variably saturated. We refer to groundwater of all water below the land surface. We do not distinguish between the vadose zone and the saturated zone. It's really one continuum from bottom to top. And this also holds actually for the connection with surface water, which is of course local. We have a connection to surface water only in certain regions. And it is actually part of the water continuum. And we treat it this way mathematically via, for example, oval and flow boundary conditions. Air, in our case, is also part of the three-phase system. Here we actually treat it also as a continuum, but we assume an infinite mobile phase. This assumption can actually be relaxed if we really need to. Okay, so the bottom line is we do not compartmentalize the subsurface and the surface water domain and couple it back later together at runtime at our models. Instead, we really treat it from the beginning as one domain and as one continuum. And that is important also to keep in mind. And this way, we actually account for all also nonlinearities. There are many examples of these types of models. We develop PowerFlow in a larger group with colleagues in the United States, also Reed Maxwell, Laura Condon, and the Lawrence Livermore colleagues. It's an open source development. It's a 3D variably saturated subsurface surface water flow code. It includes also human interventions. It's PDE based, as I mentioned. We connect also to different land surface models. We have an internal land surface model, the common land model. We have parallel reactive transport in there. And we also have an energy transport model and adaptive mesh refinement model, but they are not part of the main branch in Git. And of course, we couple to various land surface and also regional climate models. We really close the water cycle and the energy cycle from bedrock to top of atmosphere. But there we make strong use of external coupler technologies. We also do data assimilation to merge our model with observations. I will not talk about this today. And we invest a lot of time to optimize the codes on massively parallel supercomputers. I will not go into details here of PowerFlow. For the simulations I will show later or in a minute, it's important that PowerFlow has an embedded DSL approach where we can connect different accelerator backends to the code based on CUDA, COCOS, and HIP. So we have really achieved a very high degree of performance portability, which is really important when you see the new machines, the new HPC machines that are coming online. And what I also want to mention, and I will get to this at the end too, is that there are already a lot of machine learning and deep learning emulators coming online. This is mainly a development by Reed Maxwell and Laura Condon. What's important to understand if you do this with these types of models, that you can actually vary the complexity of these models. Really, you can go from a lumped simplification, which is also often part of land surface models or global water models, and you can actually increase complexity, for example, in PowerFlow step by step until you arrive really at the full 3D continuum approach that I was just talking about previously. So this is really important, and this is very nice actually for hypothesis testing. So what we do is when we do these simulations with our continuum models, we come in with a arbitrary initial condition. For example, like you see here, we initialize our water table at a certain depth below the land surface, and then we start forcing the model with our atmospheric forcing if connected to a land surface model. And then the model really approaches a dynamic equilibrium that is based on the connected physics. And what you really see is that the rivers are forming, in quotation marks, naturally. So the river corridors are appearing based on gravitational flow and topography and interaction with the land surface. And step by step, you approach this very nice dynamic equilibrium that is, let's say, physically and also with respect to solutes consistent. And that is shown here a little bit, in this animation. Okay. So the new development, what for us is really that we try to move from the watershed scale and continental scale to this global scale. Here, really, we exploit the performance portability of path flow, so we can actually move to the type of exascale or pre-exascale machines that are available today. So we are now implementing a path flow model at 1 kilometer resolution. This one has 15 vertical layers with increasing thickness, with a total depth of 60 meters. So the boundary condition here at the bedrock bottom is no flow. We actually do not have lateral boundary conditions really at the continent, but the oceans are really treated as infinite sinks. And if you have questions to that, we can talk about it. We inform our model with global hydrogeologic information and soil information, and we now perform a spin up towards steady state with an effective recharge data set based on precipitation minus actual evapotranspiration. So currently the system is running on 320 NVIDIA A100 GPUs distributed over 80 compute nodes, and we can actually achieve like a 1-year simulation in about a day, a little bit more, 1.5 days. Okay, here are some examples of input. So for hydrogeology, we use the Glimpse data set and soil grids. Soil grids we upscale to a 1 kilometer resolution. And here's an example of a mean effective recharge data set we derived from the EasyMap2B forcing data set. And we interpolated this to 1 kilometer in a rather ad hoc fashion. But for the first, let's say, proof of concept simulations, we feel that this is good enough for us. So when you do this, as I showed before over Eurocortex, you actually start with a arbitrary initial condition. You initialize, for example, the water table at a certain depth, and then you start driving the model to some dynamic equilibrium. And here, what you get out of this here is a diagnostic variable, for example, water table depth, and you see actually some general patterns that are not new to you. But for us, it's very nice to see that the model is really approaching this dynamic equilibrium in a physically consistent way without prescribing any river corridors or parameterizing exchange with the land surface. And you see really here nicely, which kind of detail actually you can achieve with these models. I feel this is, to us, it's still amazing to look at this. I can stare at this for hours, actually. So you can also then zoom in, over orders of magnitude, and you get out even more details here with respect to these kind of, overall streams. But you also see, of course, artifacts coming out because of the input data set. So in this case, really, the model is not forgiving much, if you basically have, let's say, a core scale, for example, also, for input data sets. So here we see, a zoom in over South America also, Okay, so what we are doing also with this model, we are coupling this with the global implementation of ICON. We are doing this in a project with the Max Planck Institute and the German Weather Service. So we have an implementation now. We have a nest actually where we have over the Eurocortex domain. And what we want to understand there is how resolved hydrogeology and groundwater implementation is also influencing perhaps large-scale circulation patterns. This is based on a pan-European groundwater to atmosphere terrestrial model implementation that we published previously. And ultimately, what we want to do is we want to perform next like latitude belt simulation with a full groundwater implementation, and then also full feedback simulations where we have path flow running beneath icon everywhere. To understand, is there really a non-local impact of groundwater via the global circulation? Okay, I wanna also do a shout out to the GWEX Global Groundwater Network. We initiated this over the past year with my colleague Laura Condon, and we have a steering group that is very active in trying to define a scientific agenda, how we can bring groundwater, or how we can inject groundwater in the global ESM community, and start a dialogue on, for example, also what degree of complexity is required. And so if you're interested in this topic, I would strongly encourage you to go to the website and sign up for the newsletter. We are now in the process of contacting people also bilaterally and setting up working groups that ultimately will define this scientific agenda within GWEX and GHP. So this brings me also to the end of the presentation. Just a few conclusions. I hope I can show that kilometer scale prognostic groundwater flow simulations are possible from the continental to the global scale, with all the obvious and not so obvious limitations and challenges, of course. I feel that these simulation results provide a new level of physical consistency and realism, and this is really key ultimately also for feedback simulations in ESMs. Of course, here the level of required complexity may vary depending also on the questions you want to answer. The data challenge is ubiquitous, but I argue this will never go away, and I think AI will have a great contribution in filling our information gaps. With respect to hydrogeology, how do we get hydrogeology in our models with respect to these hydrofacies distributions? I feel we need new concepts for hydrogeologic modeling, and this is something also we want to tackle in our global groundwater network. Now people are moving in terms of hardware to the exascale realm. If you actually work with these machines, and you want to use them efficiently, you realize actually that you can go even, or should go even, to higher resolution. And this means we can ultimately go to 10 to 100 meter resolution. Again, what does it mean for the data requirements? I'm just saying that, let's say, from the capacities, from the hardware capacities, we can actually do it. Hydrogeology and groundwater flow modeling is important in Earth system modeling. This brings me back to the very beginning of the presentation when we talked about this water equilibrium on the continent. The same counts actually also for active transport and biogeochemical cycles. So, you know, the continents not only have to get rid of excess water, they also have to get rid of excess solute from weathering, for example, on top of the human impacts. AI technologies, which I have not talked about much, will be key in tackling, for example, the spill-up challenge, also modeling itself and the uncertainty challenge. A good example is Hydrofame by Reed Maxwell and Laura Condon, where they provide a very nice framework to apply these types of emulators of path flow over Konus. So from my side, that's it. I have attached some references here, and I'm ready to take any questions. Thank you.
Thank you very much, Stefan, for this kind of nice introduction, and also showing this groundwater map simulations globally. That's quite impressive. Thank you very much.
Thank you.
And for the audience, you can either post your questions on the Q&A session or on the chat box, please.
Well, I think we want them on the Q&A.
Sorry, please post the questions on
Yeah,
the
put them on the
Q&A.
Q&A. So Stefan, we
Yes,
did have a
Taiwan,
question come in. Can you see the Q&A?
Yep. The Q&A, is it the chat, right?
no,
No,
not
it's
a
not the
chat,
chat.
the
There should
Q&A.
be a Q&A. Just hit a button. There's a button called Q&A that you can pop up a window.
There
I
it
can
is.
read you also the
There it
questions.
is. There it is. Yeah, sorry, I'm slow. So the first question is, oftentimes coupled models with groundwater schemes activated would be very computational time consuming, which is a particular concern for very high-res applications. Do you have any comments on using ML-based groundwater schemes? No, absolutely correct. This is computationally expensive. But I think when we started this, we were doing 3D groundwater models on a domain, let's say 1,000 by 1,000 pixels, going, and this was 15 years ago. And this was considered a large-scale simulation, right? And now we can go actually to kilometer global, and we'll be able to run this on the new machines with let's say less than 100 GPUs. So I think the computational expense is large, but it's not prohibitive. And I would agree that ML-based groundwater schemes are also another option or alternative if you don't have the compute. But first, we have to have the data sets to train our models on. And this is very different from what we observe in the atmospheric community, where we have this very computationally expensive reanalysis data sets, right? But they are the key, actually, to these very sophisticated MLDL models, of the atmosphere. Unfortunately, we do not have that for the water system on the land, well, below the land surface, and this is actually right now, I think, hindering us in making large progress with respect to MLDL based, globally, with respect to groundwater. I hope I answer your question.
Stefan, I have a follow-up to that, actually. So the power flow and producing these amazing results for generating the rivers, does that actually produce then like a stream flow, like a runoff? And can you actually validate that? And like I guess follow on, as many or most hydrology models I've seen require a lot of tuning to actually get that reasonable. And is that something that you would need to do with something like power flow too?
Right. So indeed. So we treat the water as a continuum, as I said, from bottom to top. So yes, we simulate exchange with surface water. We simulate explicitly surface water generation in rivers and base flow, and we also route the water at the land surface, in river channels, right? We do that, and yes, we always compare to discharge data, measure discharge data, GRDC, and that's a very that's one it's one part of the validation. Since we actually have, let's say in quotation marks, all variables available in our model with respect to states and fluxes, we compare also, of course, to soil moisture data. We compare to water level observations, geosymmetric depth. We compare to remote sensing data such as GRACE. If we couple to the land surface model, we can validate with all, let's say, fluxes also with respect to ET and sensible heat. What we usually do is we do not calibrate our models. These are really fully dynamic, unconstrained, uncalibrated simulations. And when you look into the publications, it's surprising how well we are actually doing in comparison to also to in situ observations. And my hypothesis is why this is happening is that by basically relaxing artificial boundary conditions that we usually have, for example, also in land surface models, and giving the model the full degrees of freedom and with respect to feedbacks, that this is actually resulting in a consistent response, including all the nonlinearity, which then results in this reasonable or very good agreement with observations, also at the local scale. Yes. Thank you.
Cool. And we have
yeah,
a
and this is also
question on Andrew.
Yeah, Andreas Brian asked this question also with respect to validation, right? And I think I alluded to this already. But of course, I mean, when you look into there are data sets available. There are also with respect to water level measurements. Of course, they are fragmented, right? So we have regions where we have very strong, where we have a strong database, but then we have basically regions where the Earth is blank. But I feel, again, you know, these types of models, they can actually be used also to fill data gaps. I think where we have ungauged regions, I think these types of models are also a reasonable tool or useful tool to interrogate the water state, you know, since we don't have anything else available. Yes. So there's another question.
Cool. Yes.
So
Cheng?
Yeah, so there is one challenging issue is Cheng, yes, thank you for the question. There is an issue with the vertical heterogeneity of parameters, riverbed depth, how much uncertainty confident we have with these data sets parameters for global groundwater patterns. Yes, this is totally right. I mean, as I said, the uncertainty in these models and in the data sets is ubiquitous. What we find actually, what is kind of interesting is when you look at the comparison also to observations, that even local heterogeneity, if you interrogate bulk mass fluxes with respect to water, local heterogeneity actually is not that important. This picture changes completely when you go to solute transport or even reactive transport, right? Then, you know, local heterogeneity always rules. But in terms of bulk water mass flow, you know, the local heterogeneity is actually not that important. That being said, is of course we need to improve our models, you know, and with respect to a 3D representation of hydrogeologic heterogeneity, you know, also at the land surface subsurface interface, you know, also at the surface water groundwater interface, right? And we can do that actually over regions. We can do that very well where we have the data set. In other parts, we have to invert for our hydraulic parameters, or we have to come up with ad hoc parameterizations ideas.
Yeah. And I think here's the second question.
Yeah, this is an anonymous attendee. Thank you for the question. So it's about a coupling of groundwater with land surface models and in ESMs in the ESM context. Yes, so of course, land surface models in system models, mainly as lower boundary conditions for the atmosphere. They work with also the shallow subsurface zone, which is commonly referred to as the soil zone. And often, at least these global scale models have only treat flux in the subsurface 1D only, and with a simplified boundary conditions at the bottom, often a gravity drainage. And this is exactly what I meant before, that there are artificial boundary conditions like this free drainage boundary conditions in these models, and they have a huge impact then on the response, you know, in the soil layers and above. And that's exactly what we want to, that's exactly what we want to improve. So when we couple to land surface models and then also to the atmospheric models, what we do is we replace the hydrology in these land surface models completely and replace them with our continuum approach. So then the water is redistributed in the subsurface by power flow, for example, and then connected with land surface processes via sink source terms, evapotranspiration, precipitation, infiltration, and so on. Yeah,
And
so
the next one by Sohai.
so yeah, thank you for the question. Given that extrapolation is not really what MLAI are meant for, how efficient would you think a hybrid system would tackle this, especially for spinner purposes with LSM? Any known example? Yes, this is a good point here. The extrapolation challenge, or let's say MLAI, and I agree here, are not meant for extrapolation. Even if people say with this large degree of generalization, maybe now you can go into extrapolation. In my personal opinion, I would still doubt this. A hybrid approach, yes, this could be very promising, and Xiaopeng Shen, for example, is working in this direction. And I would be more than happy to talk about this in more detail and maybe try some things out. Yes. Examples, yes. I think the hybrid models currently are also more related to more simplified hydrologic models, which represent the physics. I have actually not seen a true hybrid model which is based on a PDE approach in connection with MLDL. No, but I might have missed it.
Okay, well, thanks, Stefan, for answering those questions. May I have one about that you mentioned using the ocean become like infinite states. So I wonder whether this path flow model globally can help us to simulate this submarine discharge. Is that possible?
Currently, what I meant by infinite sink is that we do not prescribe any kind of boundary condition along the continental margins. Okay, so meaning there is not a prescribed, for example, Dirichlet boundary condition or Neumann boundary condition. So there is actually a free exchange of flow into the into something like an ocean. There are, of course, models that also simulate exchange with the ocean and seawater intrusion. You cannot do this with path flow at the moment. Could you actually have a full continuum model from the continent into the ocean, also representing the continental shelves and continuity of seawater and groundwater in the continent? Yes, in my opinion, you could do this. But I have not seen such a model in practice yet.
I see. Because that's one of those missing components about how much groundwater, the submarine discharge.
But I mean, for example, ModFlow, for example, has this capability. There are other models that can actually do this in terms of seawater intrusion and exchange. I mean, we get some bulk estimates out of this from our model, but we have never looked into any kind of validation with respect to these fluxes. No.
I see. Gotcha. Thank you.
Mm-hmm.
Do we have other questions? Well, probably not. Well, thank you very much. I think this is our first time to touch this high-resolution groundwater model in this webinar series. That still a lot of challenges, especially the data. How we can get the good data for the subsurface is still a lot of effort need to be done.
Yes.
Okay. Thanks everyone joining, and I think it's a nice discussion. Especially thanks Stefan to give us this wonderful talk and discussions.
Thank you.
And we will have another one in first or second week of April, and we will announce it sometime soon. With that, I would close this webinar, and I will looking forward to seeing you soon again.